All right, welcome back. So, we've already talked about the big guys Newton, Einstein. That's the foundation, right? But physics, it never just stops. The really exciting question is okay, what comes next? What happens if we stop treating gravity like a closed book and start looking at it as an active mystery? That's what we're doing today. We're heading to the frontier, checking out some wild ideas that might just be the next chapter in how we see the universe. So, let's kick things off with a question that kind of messes with your head. We're all taught that gravity is one of the four fundamental forces of nature, period. But what if it's not? What if gravity is more like an illusion? A shadow on the wall that's hinting on something much, much weirder happening at a deeper level. Okay, so here's the game plan. We're going to look at three main, let's call them flavors of these new theories. First up, could gravity just be a massive, zoomed out version of an electromagnetic effect? Second, what if it's not a pull at all, but a push, driven by the universe's love for chaos? And third, maybe it's just a property of empty space itself. After that, we'll get into the fun part. Can we actually test any of this stuff? And then we'll pull it all together to see what this new picture of gravity looks like.
The big idea that ties all this together is called emergent gravity. And honestly, the best way to think about it is to picture a flock of birds. It's amazing, right? They create these incredible, complex patterns, but there's no leader yelling out commands. That pattern emerges from each bird following a few super simple rules. Well, emergent gravity theories are saying that the force we feel is just like that pattern. It's this huge macroscopic effect that comes from a kind of swarm behavior happening on a tiny quantum scale we can't see.
All right, first stop on our tour, let's explore this idea that gravity might be secretly related to a force we know inside and out, electromagnetism. The big question here is, could gravity be a huge cosmic side effect of quantum potentials that we've just been looking at the wrong way this whole time? So this whole line of thinking is called gauge theory gravity. And here's the gist. It suggests that a big chunk of mass, which remember is just a giant pile of charged particles like quarks and electrons, creates this kind of potential field that fills up all of space. In this picture, a planet doesn't fall because space-time is bent. No, it falls because it's just trying to find the lowest energy spot in this universal field. It's kind of like a marble rolling to the bottom of a big invisible bowl. Okay, but right away, there's a huge problem with this idea, a really obvious one. If this whole thing is based on electromagnetism, why does gravity affect things with no electric charge, like a neutron? This is called the neutrality problem, and it's a massive hurdle for any theory that tries to link these two forces. And this is where it gets really clever. The defense on this slide basically says, hold on, neutral is just an approximation. A neutron isn't some solid neutral billiard ball. It's made of quarks, and quarks do have charge. So the argument is that this gravitational potential is so fundamental, it can actually feel that internal charge structure. Or, and this is even cooler, maybe it doesn't even pull on the neutron directly. Maybe it polarizes the vacuum of space around the neutron, and the neutron is just along for the ride, following the changes in the energy of space itself. All right, attack number 2, the shielding problem. We can block electric fields really easily. You just build a metal box, a Faraday cage, and you're done. So if gravity is a similar kind of potential, why can't we build a gravity shield? Why does it seem to just go through everything, completely unstoppable? And this slide just brilliantly nails the counter-argument. It's that we're thinking about shielding all wrong. A potential isn't some thing that's traveling through the wall of your shield. The potential is the state of space that the wall is sitting in. It's like trying to build a box on a boat to shield yourself from the ocean's water level. You can't. You're already in it. You can't block the fundamental energy level of the universe itself. The potential isn't local, it's everywhere, all at once. So this really gets to the heart of it. It's a total shift in how we see things. Einstein's general relativity says mass tells space-time how to curve, but these new ideas, they say mass tells the vacuum how to fill up with potential energy. Now, both of these can predict an orbit pretty well, but the picture of the universe they paint is radically different. One is a universe of pure geometry. The other is a universe that's more like a giant interconnected electrical circuit. Okay, let's shift gears to our second idea, and this one's even more out there. What if gravity isn't a pull force at all? What if it's actually a push, and it's driven by the most basic tendency in the entire universe? The unstoppable drive towards chaos and disorder? This is the core idea behind entropic gravity. And entropy, well, it's just a fancy word for disorder.
A tidy room has low entropy, a messy room has high entropy. And one of the most fundamental laws of physics, the second law of thermodynamics, says that the total entropy, the total messiness of the universe is always going up. Entropic gravity just takes this one step further and says, hey, maybe that force we call gravity is just a direct result of this law. It's not a fundamental force. It's just what happens because of statistics.
So how on earth could that work? Well, one model asks you to imagine that space is filled with these tiny quantum bits, qubits, and they're all pointing in totally random directions. That's maximum chaos, maximum entropy. Now, you drop a massive object in there. Its presence forces all the nearby qubits to line up in an orderly way. Suddenly you have this little bubble of order in a sea of chaos. Now, put a second mass nearby. You get a second bubble of order. And the universe hates this order. It wants to be messy. So to maximize the overall disorder, the system creates a pressure that pushes these two masses together. Why? Because that shrinks the size of the ordered bubbles, letting more of the universe go back to being random. The attraction we feel is actually a push from the outside in.
All right, on to our third and final theme, and this one kind of pulls together some of the threads we've already seen. What if the real key isn't electromagnetism or entropy, but the nature of the vacuum itself? What if empty space isn't empty? What if it's a real substance, a medium that can be stretched, stressed, and even thickened? This slide lays out a direct comparison pretty nicely. In what's called the capacitive vacuum model, space is basically filled with a super thin gas of hydrogen and neutrons. This gas acts like the insulator in a capacitor. In this view, gravity isn't a pull, it's the stress within this medium. A planet orbiting the sun isn't falling through curved spacetime, it's floating on lines of equal potential in this medium, kind of like a boat following the contours of the water. And what's really fascinating is that this model actually allows for gravitational repulsion, something that's pretty much a no-go in general relativity. Okay, now, this is where things get really wild. A theory called G4V makes an absolutely stunning claim. The speed of light, c, is not a universal constant. It actually changes depending on how strong gravity is. And the reason why is even crazier. In this model, the speed of light is the local gravitational potential. They're not just related, they're the exact same thing. So what this does is it completely changes our view of gravity from geometry to optics. A huge object like the sun doesn't curve space, it makes the vacuum around it thicker, more optically dense. It literally increases the vacuum's refractive index. So light bends around the sun for the same reason a straw looks bent in a glass of water. The medium it's moving through has changed. Even time slows down because, in this view, matter waves just oscillate more slowly when they're in this denser medium. Look, all of this is incredibly cool to think about, but in physics, a theory is just a nice story unless you can test it. So let's see how these really abstract ideas might actually lead to real experiments. Can we actually see any of these effects in a lab? And the answer is a resounding yes. This right here is a diagram of the famous Colella-Overhauser-Werner experiment from way back in 1975. And what they did was just brilliant. They built a machine that could split a single neutron's wave function into two separate paths. Then, they just raised one of those paths a tiny bit higher in Earth's gravitational field. And when they brought the paths back together, they saw a measurable, predictable shift in the neutron's quantum phase. This was it, the first direct proof that gravity isn't just a classical force for planets and apples. It operates directly on the weirdness of the quantum level. Okay, now things get a little more ambitious, and honestly, a lot more controversial. Back in the 90s, a researcher named Eugene Podkletnov published experiments claiming he could reduce the weight of objects by up to 2% just by spinning a superconductor underneath them. Now, let's be super clear. These results have never been reliably replicated, so we have to take this with a huge grain of salt. But just think about what it implies. It hints at the incredible possibility that if gravity is an emergent field, then maybe, just maybe, one day we could learn to engineer it. And that's the real why this matters moment. It's the difference between gravity being an unchangeable law of nature and being a brand new frontier for technology. So we've looked at gauge theories, entropic forces, the vacuum as a medium. They all sound pretty different, right? But if you take a step back and squint a little, you can see a common picture starting to form. What's the thread that ties all these wild ideas together? Well, across all these different models, 4 big themes keep popping up, and together they paint a really consistent, alternative picture of gravity.
First, gravity is not some mysterious pull from a distance. It's a push or a pressure from the outside in. Second, the vacuum of space isn't empty. It's a dynamic, physical medium with properties that can change. Third, the classical gravity we experience every day emerges from a deeper, statistical, and fundamentally quantum reality. And finally, maybe mass isn't something a thing has, but is really just a measure of how strongly that thing interacts with this vacuum medium.
And that leaves us with one last thought to chew on. For more than 100 years, we've thought of gravity as this fundamental pillar of reality. But if any of these theories are on the right track, it might just be the first, most obvious pattern to emerge from the chaos of the quantum foam. And that just makes you wonder, if gravity is just the first thing to bubble up, what else is still down there, waiting to be discovered?